that's not what I want. Our plan is to go over chapter 5 homework number 2, and then we have 2 sections of notes today that hopefully together they shouldn't take that long. So I'll stop talking and let me get started here. Chapter 5 homework number 2 is an important one. The kinds of things you're doing on this assignment are the kinds of things you're going to be tested on. I wrote your test yesterday afternoon, so it's nice and fresh in my mind. So as we go over this homework assignment, I will do everything I can to point out the test questions. My biggest fear with your test is that when you see a question like number 7, is that because it's embedded into a FRQ style question, that then all of a sudden what you already understand how to do goes out the window, right? So when you're taking your test and there's a big paragraph that describes an experiment, and then part 1 says something like what you see here on number 7, treat the question as if it's its own problem, right? So in your big paragraph, there's going to be some given information, just like this one has it nice and concise in one line. Try to see if you can separate that out of the paragraph. Maybe write it down on the corner of the page. Remember that I give partial credit. So if you can't figure anything out, but you've written down all your givens, I'm going to give you some points towards that. And speaking of points towards that, you guys probably have recognized that that yesterday I sent you a post telling us that today we were going to be Zooming right now. And on that post, I included an exit quiz today. So it's possible some of you have already filled it out. It's quick. Really all it is it's just a legal thing so that if you don't attend my test on the day that I say, here's the test, that I can do everything I can to make sure that you get a bad score on it, right? That if I pass out your test, and see, this really hasn't happened with this class. You guys are all doing everything exactly as I want you to, but like I had a test in regular physics that I put out, and the kid turned it in 5 hours later, right? And it's like, come on, what's that about? So I want to be able to talk to you on Zoom while you guys are taking your test. I'm not going to bug you while you're taking your test. All your names are going to be there. I'm going to be over here, grading emails, homeworks, and things like that. You're going to just keep taking your test. But then when I start feeling like, the first tests get turned in, and I look to see that person who turned in the first test completed everything, so I know that it's, a legitimate amount of time, then I'm going to start telling everybody else, okay, you've got a half an hour, and that you need to get the test done, and so that we can keep them in a reasonable amount of time. And then I want to reward you for it. So the fact that you are coming to these Zooms, maybe like Yvette does, she says good morning and lets me know that she's there. You could do those kinds of things, and I'm going to just keep adding those to your test curve. So that's the plan. But I don't want to keep you guys here from 8 to 9:30. We should be able to get through the notes as quickly as it takes to get through the notes. So therefore, I'm going to stop talking. But I needed to tell you that in case you were wondering what that whole exit quiz was all about. And I will count that exit quiz. I'll make it worth like 3 points. And so you should get a 3 out of 3 as long as you just submit it back to me. All right, so you're taking a test and you get to part A of question number 7 on the test, and it says what volume. So right away you're thinking what volume, V equals question mark. Then you see a bunch of givens that were written up into the paragraph, and so you write down that the mass was equal to 2 grams, that the temperature was equal to 25 degrees Celsius, and the pressure was equal to 775 millimeters of mercury. And while we're on this topic, I probably will convert millimeters of mercury into atmospheres because I like to use latim per mole. But on the test, as I was making the key, it actually was easier to use Latour per mole because this value here is given as millimeters of mercury, which is commonly known as torr. And since every part of the problem all deals in torr, it's just easier to use the number that says, I think it's 62.4. I know it's 62. I just can never remember if it's 62.8, 62.3, 62.4. It's one of those numbers, but it's on your cheat sheet. And quite honestly, if you rounded it to 62, it wouldn't hurt my feelings anyway. But that would be the ideal gas law constant in Latour per mole. And I'm just telling you ahead of time that on your chapter test, it would just be easier to use that one. So you have fewer things that you have to convert. But since on my slides, which you've already looked at, I've already converted this to atmospheres, I'm sure. Just be prepared that that's what I'm going to do. Okay, so I want to find a volume. So now we have to think about what ways do we know how to find volume. So our possibilities that we have, and remember, all of this stuff could be written down on your test question, and I'm going to give you partial credit accordingly. So PV equals nRT, PVT equals PVT, and as we've learned by watching my video lessons from the first day, these are really the same equation. What these imply, the combined gas law, which is, we'll call this number 2, and this is number 1. Pubnert is number 1, combined gas law is number 2. We learned that really what combined gas law is in a closed system, like, for example, our good old-fashioned cylinder of science. When you trap a gas inside of there, the number of moles can't change. So if the moles is held constant as you move the piston in and out in order to make a smaller volume, or if you apply a flame in order to heat this up, other variables have to adjust for the fact that you've changed one of them because N has to stay a constant. But of course, we also could add into the combined gas law and really make it a true Pubnert, is that if we put the N in here also, now we could actually put a valve on the side of the container and we could squirt some more moles of gas in there if we want to. So these are really the same thing. It's just that number 2 kind of deals with a closed system, okay? Then the third one that we could say is we could also talk about stoichiometry, and then at some point in time, use a conversion that gets out of moles and gets into liters. So really, those are our 3 options on how we would end up with getting an answer that comes out to be volume. All right, so your job, knowing that these are your 3 options, is to go back into the givens and say, okay, which does this fit the best? And quite honestly, you could either go with number 1 or number 3. And really, if you're going to use number 1, no, I'm sorry. If you're going to use number 3, then it's going to require you to take this answer and then go back and do a number 2. Because, that sounded funny, because of the fact that you have to do an adjustment. This was at STP, and these conditions are not at STP. So I'm going to use number 1 as my way of doing this. Now, if I'm going to do number 1, that means that volume equals nRT. I should do this in an official color. Volume equals nRT over P. Okay, so now if I'm going to use that, my issue is I need to convert 2 grams of oxygen into moles of oxygen. So I still do need to do these first 2 steps of the stoichiometry. It's all interrelated, isn't it? It's like when you're in biology class and you're learning about the web of life. This is the web of chemistry, is that everything seems to relate to moles. And then from moles, you can go anywhere you want to. So if I do the first 2 steps of this conversion table, that's what it comes out to be, 0.125. Kumar's trying to speed me up here. You're probably right. Getting out of grams of O2. Do you have an issue on your test where you need to know a substance chemical formula? I don't believe so. I think that on all of the tests, I give you all the chemical formulas. It's possible on what I call the Chapter 5 makeup test that it could be written out like this, and then that way I could take points off of the people who didn't take the test on normal time by the fact that some people might forget that oxygen is O2 and write it as just an individual O. So we're going to get out of grams and get into moles. So it's 32, not 16. And then I'm going to believe Kumar because he put 0.125 in my chat. So I'm going to go with that, 0.125 moles. Then the ideal gas law constant, since on the next slide, I'm going to change it to atmospheres. I'm going to cheat. Oh, hey, I've already got all that stuff written out here anyway, so I'll just leave it on this slide. Yeah, well, I went to sleep about 8:30. I had a couple beers last night, but not very many. I should feel great today. I feel lousy. It just shows, your body gets used to the way you treat it, and then you should just keep treating it that way. 0.0625 moles is what I have here. I'm not sure why I'm putting it in parentheses, but it's too late now. And then I'm going to put the ideal gas law constant here because I changed into atmospheres at 1.02 atmospheres. That means that I have to use the units latam per mole. And that one uses 0.082. The only reason I did that is because when I was writing these notes 5 years ago, your textbook always switched into latam per mole. Your textbook always used 0.082. So as a person who was a 20-year chemistry teacher, but never been an AP chemistry teacher or college professor, I thought, oh, I have to do that, right? So I just kept doing whatever your textbook did. But now that I've been grading so many years of AP tests, the AP test doesn't do that. They use whatever unit is convenient. So you do whatever it is that you want. I'll know, but showing your work is always a good idea. And then over here, the temperature 25 is 298 Kelvin. All right, so now let's look at the units. There are moles in the denominator right here. So those moles will cancel out these moles. There is Kelvin in the denominator here. So those Kelvin will cancel out these Kelvin. Now, if I were to rewrite this, it would say 0.0625 with no units times 0.082. Oh, I don't want that in parentheses yet, with the units of latam, no bottom, because we already canceled that out, times 298. Then in the denominator, it would be 1.02 atmospheres. So now it might be easier to see why the atmospheres also cancel out here, because a numerator in the numerator cancels out a numerator in the denominator. Now the only unit that's left that hasn't canceled out is the liters. If that step confused you at all, forget about it. On the AP test, they don't grade that these units are inside the problem, so I won't either. The only thing that you're going to be graded on is that your final answer has the correct number of significant digits and also has the unit attached to it. So if you know that the answer is supposed to be in liters and you did everything with the proper SI units, then you know that that's your answer and you're done. And as far as significant digits go, I get a -1 point because with 2.0 grams, this should just be 1.5 liters. Okay. Question number 8. An ideal gas is contained in a cylinder with a volume of 500 milliliters at a temperature of 30 degrees Celsius, and the pressure inside of this container right now is 700 torr. The gas is then compressed to 25 mils, so I'm going to compress this all the way down, just like inside of an engine. In fact, I think on one of your test questions, I even, so that you couldn't just look up the AP FRQ that it came from, I just changed the way the words are, right? I've watched my wife enough to know that in Spanish class, it's a very small percentage of her students are just dirty little cheaters, and all they do is just type into Google Translate. So you would do the same thing, wouldn't you? Wouldn't you just type in the first 10 words here? An ideal gas is contained in the cylinder with a volume of 500 mils, and bam, the FRQ that this came from pops up. And then you're like, oh, okay, I see how to do this. So I just change it so that it's written in some way that Google wouldn't be able to figure that out. But I promise you that if you go print out all of the AP FRQs, you should be able to find one that's very similar to whatever I do. Don't waste your time. Practice, but at the same time, I'm giving you the FRQs that are just like it. So your lab that's coming out on Wednesday, there's a test question that's just like it. All right. I see a closed system. So because there's this closed system inside of our cylinder, we have, with our piston inside of here, we have a set number of moles. And so therefore, when you squish those moles, N still equals N. So therefore, I can then go to just the combined gas law and say VPT, set them equal to each other, and solve for the P that's missing, okay? And then, hey, you know what? You guys were the smart ones in my chemistry class when I kept talking about this kind of stuff. You should be able to look at your answer and go, does that sound right? Does it sound like if you had a gas that was trapped inside this really large container and you all of a sudden slammed this piston down and made the gas into a really small volume, and meantime, you also increase the temperature of it 3 times greater, do you think you should have gas that has a really, really high pressure? I would hope you would say, well, shoot, it should be tremendously high pressure. We've decreased the volume by like 20 times, which would cause, I'm sorry, yeah, we decrease the volume by about 20 times. Hopefully I did my math right there. That should cause the pressure to go up by 20 times. So I would be thinking like 14,000. Then we increase the temperature by 3 times. So 14,000's got to increase by 3 times greater. I think 51,000 is pretty close to 3 times greater than 14,000. Am I speaking outside of anybody's abilities? I don't think so. Question number 9. What mass of helium is required to fill a 1.5 liter balloon? Remember that this would not be showing up on a test, so it'd be your job to sit there and write down what mass, so question mark, grams, or however you would write this. M equals question mark is how I would do it, I guess. I'm just kind of writing all over the place. Question mark number of grams. And then they talked about a volume of 1.5 liters, a temperature of 273 Kelvin, and a pressure of, now it really depends up what you want to use. If this was last year, you probably would pick 101.3 kPa. That's fine. Then just be prepared that you're going to use 8.31 lakappa/mol. If you choose to use 1 atmosphere, which is easier math, then you're going to use 0.082 latam/mol. Once you do this, you're going to solve for N. And then once you have the N, we just need to convert it into M, convert it into mass. Okay. Question number 10. At this point in time, somebody might say to me, do we need to use all of those digits? No, just use 0.082. The only reason I did this is because, like I said, your textbook did. So I thought I had to. And so some of the problems that were ones I worked out ahead of time 5 years ago still show the whole decimal, and the ones that I've worked out more recently just stop at 0.082 because that's what I think your cheat sheet does also. A student adds 4 grams of dry ice to an empty balloon. What will be the volume of the balloon at STP after all of the dry ice sublimes? So you have the same choice here right now. Back to our very first problem that you could say what volume is nRT over P. But then the other thing is they told us at STP. So you also could just do a conversion table that starts with the 4 grams, gets out of the grams of CO2, which is what I just did above. Then on my last step is get out of moles of CO2 and get into liters of CO2. Right? So if you're sitting there going, but Mr. Purser, which one should I do? What would you choose on the test? Both get exactly the same points. So you get to choose what you want to do. So do what you want to do. On this one, I chose, well, I wrote them both down. So there they are. I don't know why I broke this up into 2 conversion tables. I guess it's because I needed to know the moles in order to do the Pubnert way. But if I had been just working this out stoichiometrically, then I would have just kept that conversion table going. So far, so good. Question number 11, calculate the volume of oxygen at STP required for the complete combustion of 125 grams of octane to CO2 and H2O. A question like this, of course, would be accompanied with a balanced, well, maybe not balanced, but with an equation. And then as you look this over, you're thinking to yourself, okay, now what exactly am I trying to find out here? Calculate the volume of O2 that's needed. And I want to have the complete combustion, which means that I think that I want to use this up. Use this up. Okay? So, I don't know. I think that the best way to look at this one is to think of this as just a stoichiometry problem that is going from grams and takes us over to liters. And in order to get there, we know that because it's using a balanced equation, pretty much every time we see a balanced equation, it's a 4-step conversion table, right? And, you know, enough of these practice that you guys start going, there's a process every single time. I could be a robot. We could teach Google how to solve these problems because they always follow certain rules. So if this is what we're going to go with, grams of octane, C8H18, 125 grams of it. We'll get out of the grams there And yes, and then we're going to work towards liters. So I'm going to have to go to the next slide to find out what those numbers are, but at least I can put this much in here. And the reason why I'm putting this in here is because this step right here is our first issue. The mole to mole ratio would have to be figured out by balancing this. I'm also going to go to the next slide for that. Then the last step is moles of O2, liters of O2. You can only use 22.4 when you're doing this at STP. So if the problem had not been at STP, once I get an answer at STP, I'd have to do a combined gas law to convert it over to whatever the conditions are, okay? But we don't have to do that. There's the balance, there's the numbers, and that is at STP. I'm going to repeat that statement, though, for those of you who are like, what is he talking about? It's too early in the morning for me right now. I haven't gotten up at 8 o'clock in, I don't know how many weeks we've been at school, 10 weeks, plus also all the way to last year. This is the first time you've been up this early. If this is at STP and they said that we were doing this at, let's say, 25 degrees Celsius and 200 kilopascals or something like that, then we would have to take this and go V1 P1 over T1 equals V2 P2 over T2, and then take our 307 liters times a pressure of, I'll just keep it in kilopascals, 101.3 divided by 298 Kelvin equals what will be the new volume at a pressure of 200 kilopascals and a temperature of, I already screwed that up. This was at STP. I knew something didn't feel right. At STP, these are 307 liters. Now we're converting it to 298, and then you'd finish the problem off. So you kind of see the progression of the steps if it's not at STP. The method used by Joseph Priestley to obtain oxygen made use of the thermal decomposition of mercuric oxide. What volume of oxygen gas measured at 30 degrees and 725 can be produced from the complete decomposition of 4.10 grams of mercuric oxide? I think I could have saved that last discussion for this problem because this is exactly what we have to do here. First thing I got to do is I see a chemical equation. So to get from grams to liters, I think I need a 4-step conversion table. Get out of the grams, get into the moles. Get out of the moles, get into the moles of the other substance. Get out of the moles, get into the liters, right? That common steps of a chemical equation is a 4-step conversion table. Once you get that answer is at STP because I'm using 22.4. So therefore, once I do that, then I'm going to do the combined gas law to convert to these conditions instead. And that's what you see here on step 2 of this one. Don't take these problems lightly. If you're solving these on your homework by doing solving by reading, in other words, using my slides, make sure that you look this over and go, okay, I recognize how the process of this works because that's a real life experience. This is what a lab question has to do. A lab question, usually a lab question goes opposite of this because usually the lab question is that you have to convert it to STP conditions and then maybe compare it. Like this would be the theoretical is how much oxygen should be produced, and then the actual experiment produces something else. But when you do the experiment and you have some experimental V1, the problem is if it's at 30 degrees Celsius and 725, the volume inside of here is not the same as what it would be at STP, so it's not comparable to 0.212 liters. So you have to do a conversion into STP, which is exactly what your lab on Wednesday does. Airbags are activated when a severe impact causes a steel ball to compress a spring and ignite a detonator cap. This causes sodium azide to decompose explosively according to the following reaction, which is down here. What mass of NaN3 must be reacted in order to inflate an airbag to 70 liters at STP? Same thing. This just looks like we're going to start with liters and work our way to grams. If it's at STP already, my step 2, 70 liters, will be to get out of liters and get into moles. All right? See how quickly my brain went to that? I believe your guys' brains can go that quickly too. You just got to practice. So anyway, finishing that one off, pretty straightforward. All right, today's notes. While you're copying that down, I'm going to go get myself a cup of tea and maybe a jacket because, you know, it's like what? The temperature outside is like what, 40? And then they have the air conditioners going right now. All right, molar mass of a gas. So in the end, if you've already looked at the notes of all of this, I believe that my notes do a way, way better job than I'm about to do right now. But I think it's nice to hear somebody say it out loud so that if you go back and read it, or if you were confused by it, that should clear up the confusion so that you can see the steps. And then also we need to what's the adjective I'm looking for? Make sure you recognize, that's not the adjective I was looking for, how important this is, because what we have is a gas that was created inside of here, maybe by a chemical reaction or whatever. Maybe it's just that somebody put a gas inside this container and we want to know what it is. I mean, isn't that one of the fundamental reasons for chemistry, is to know what the substance is inside of this container right here? What gas is in there? So let's think about what we have here. You have a gas that you know what pressure it's at. Maybe it could be that it's just that this equalizes so that we know that it's at atmospheric pressure in there. We know there's a set number of moles inside of here. We just don't know maybe what that is yet. We know what temperature it's at because we can measure the temperature of this very easily. Temperature of the surroundings if you let it go to room temperature. And also we know what volume it's at because the container has a set shape possibly. You know, the piston right now, I have it set at the 400 milliliter mark. I don't know if you can see that or not. Doesn't matter. And we want to know what gas is in there. So it would make sense that even though molar mass of a gas says that at STP, all gases occupy the same volume, that doesn't mean that all gases occupying the same volume have the same weight, right? Each gas is going to have a weight based on its molar mass. So if I weigh this container empty, and then I weigh this container once it's full of a gas, I should be able to use the weight and the volume as a way to figure out who's in here. What gas is this? So that's the whole point of molar mass of a gas. Now you can miss that whole point and it doesn't really matter because you'll know you're going to use this problem based on the givens that are there, because that's the way we cheat chemistry, is we just use the givens that are present to solve a problem. But I did walk through the steps of how this equation gets derived. I can try to butcher it for you right now. I think the steps that I take is, first thing I do is I define, we know from stoichiometry that if you had, so this is the part where I could screw it up because I could put things in the wrong order. If we know that, that molar mass, I know I used oxygen as an example. So I think what I did is I put 10 grams of oxygen, and then I said that if the molar mass of oxygen is 32.0 grams per 1 mole, that this step right here is the molar mass, and this step right here is just the mass itself. And then what we get is the number of moles by doing this math. That tells us that mass times molar mass equals moles. Okay, so I'm not sure that I'm going to be happy with trying to substitute into this equation using this, which is why I made the slides, because that way I could think it out ahead of time without screwing it up. But maybe I wrote down some stuff to help myself out. I didn't. I just skipped straight to the formula for it. So if you want to know how this formula derives, you might want to spend some time with that. Maybe I could say a few things here. I mean, I can always try. I mean, what's the worst that's going to happen? This is just going to be recorded on the internet forever, and everybody's going to be like, man, that teacher teaches math, physics, and chemistry, and he can't do a simple substitution? All right, I'll try, just because you guys pushed me. So P times V equals, if we say that this is equal to mass times molar mass, what I did is I just substituted in, oh, no, that's the mistake I made. Now I see why this is not working. I didn't multiply mass times molar mass. I divided by molar mass. This step right here is a division step. I put it as a time step. I knew something didn't smell right. So mass divided by molar mass becomes moles. That's what I was supposed to say. Now I feel good, because now I can say mass over molar mass times R times T. That's the substitution. All right, now I'll get this right. Okay, so now the next thing I'm going to do is, since we're going to be using gas density, I need a density unit. And what we know from the very beginning of the year last year, and we saw at the beginning of the year this year, is that density is mass divided by volume. So I'm going to divide volume to the other side. Meanwhile, I'm also going to get rid of molar mass by multiplying it to the other side. Did I do that on the slides though? Because in the end, I'm going to just do it now. I don't think I did it this way on the slides, but this will still work. So when I multiply molar mass to the other side, what I end up with is molar mass times pressure equals mass divided by volume and also R times T. Well, this right here is density. Okay, so now my next step is I'm going to divide the pressure to the other side, and I get molar mass. This is not nearly as pretty as how I did this on the slides. Molar mass is equal to density. I used a little d because your textbook did, times R times, I put an equal sign. Density times R times T over P. Okay, so now what's the importance of this? We have a gas that's trapped inside this container. We know its pressure because we can read that with a gauge. We know its temperature because we can read that with a thermometer. We know its ideal gas law constant because it's a constant. So all we have to do is say, okay, what's the size of the container and what does it weigh? And its mass divided by its volume is its density. So now we have all the information to tell us what is the molar mass of the gas. If it comes out to be 32.0 as the answer, you would say, I bet it's oxygen inside of there, right? So you could figure out what gas it is by doing this equation and an experiment based on it. Good times? There's the equation for those of you who've been waiting or who already had jumped to the punchline. Wow, look at this. I think we got everybody in here. Some of you that came a little bit later, just so you know, I said at the beginning before you got here that you could show me your homework assignment in the chat, but with your video. Just turn your video on with your homework there, but you have to do that before 8 o'clock. So after 8 o'clock, it's already late. So you can still show me at the end of the period. Days where I'm in a better mood, I probably will still give you full credit, and days where I'm in a bad mood, I'll give you half credit. Today's a bad mood day. Why? I hate bad weather. 2, found a dead chicken in my backyard this morning. 3, had to come to work. 4, what other reasons could I be in a bad mood? I think that's pretty much it. Oh, I pulled a groin muscle this weekend, installing grass in my backyard. So I had to keep climbing up into my trailer to pull the rolls of sod out, and 25 of them later, my groin's still hurting. Are you supposed to write this down? I mean, I would say that you should write down anything. The only reason I don't stay at home to do my work is because my mom, that was a Freudian slip right there. My mom lives up the street from me, just so you know. But my wife lives with me, and my wife is also on Zoom. And so it would be difficult for both of us to do it without one of us going into a different room. And we set up our at-home offices in the same room. And it would be confusing. You guys would be hearing Spanish going on in the background, and I would be hearing, or no, that's what we'd be hearing. They'd be hearing chemistry going on in the background. But if she had any students that were taking AP chemistry, and if I have any students that are taking, I don't know what she teaches first period, but you know, if like Spanish 4 and you're in Spanish 4, then you know, you get both lessons at the same time. That'd be pretty good, huh? I like coming into my classroom because then I feel like if there's something that I need, then it's here, right? Where at home, I don't keep anything there. So if we need to get out the cylinder, our gas cylinder of science, it's here. I don't have to try to go make one up at home using a piece of Tupperware. But it's weird here today. It's really weird, because today's the first day that there must be kids back at school. And so everything's locked up. I got here this morning, I couldn't get into the student parking lot. It was all closed. I go around to the teacher's parking lot. I couldn't get in. I had to go through security. And one of the security guards, I've worked with this person for at least 10 years. And that security guard looked up at me like, who the hell are you? Right? And I said my name, and I'll bet you they still probably were like, yeah, that doesn't change anything. I don't know who Mr. Purser is, right? So, but they did buzz me in, so I didn't bother wasting any time. I was wearing a mask, you know, had a beanie on and a mask on, so I obviously don't look the same as I would normally, but still, it's like, come on. I recognize you. You're wearing your mask. You don't recognize me? Yeah, I think that special ed's the ones that are here today, and so they, you know, I think it's a good idea that we lock schools up when you're at school, because we don't want people from the community to be able to get on campus while our kids are here. That's just smart, it's sensible. The density of a gas was measured at 1.5 atmospheres, 27 degrees Celsius, and found to be this number. Calculate the molar mass of the gas. So it still comes down to, even though we already know what equation we're going to be using, on test day, you don't necessarily have that ease, right? Because any question could be offered at any time during the FRQs. So your job would be to say, okay, so molar mass is my question mark. We don't really have a variable for that. I usually just abbreviate it as MM for molar mass, obviously. And then they gave us a volume as that's a pressure. They gave us a pressure is 1.5 atmospheres. They gave us a temperature of 27 degrees Celsius. I told you all those things. I'm in a bad mood, and not one person said, oh, your poor chicken. I know. It was a little baby chick, too. This week is their first week that they had to spend outside in the big chicken coop. And my guess is last night that it got really cold, and possibly that one little chick, you know, they've already shown to me that they know how to get up into the coop. Well, one of them probably got confused and couldn't figure it out, and so it slept outside, and it probably, without the other little chicks to be around, probably didn't have enough body heat to survive the temperature and died. And then something ate it. I'm guessing a rat started gnawing on it. I can't figure out what else would eat it, because if it was like a bobcat, I don't know how it would have got in my coop, because I've got this thing like, it's like being in Fort Knox in there. So it had to be something small that could fit through the chain link. So the only thing I can think of is a rat, because like a squirrel wouldn't eat meat, and a rabbit wouldn't eat meat. So the only thing I can think of is a rat, unless you guys got any ideas. But you used to live by Fort Knox? You know, I've seen pictures of it, like on that Smithsonian Aerial America, and it looks kind of neat, but I don't know. You know, rumors out there that say that all the gold that we claim that we have in Fort Knox isn't actually there. that slowly over the last like 40 years, our presidents have been selling it off to help pay bills. And that when we say that our money is represented by a certain amount of gold, that we're actually lying and that we don't have as much gold as we say we do, that makes me nervous. A lot of things make me nervous, but that definitely makes me nervous. And don't blame Humpty for this one. This is every president would have done this. Every president has to pay bills. Every president has contributed to us being in more debt, except for Clinton. And so we are where we are. Enough talking. Molar mass equals, yeah, you don't want to know what's going on. True. You probably know more than me because if you lived near it, you probably heard all of the urban legends that went on around it. Density times ideal gas law constant times dirt over P. That's right. Because remember, we always try to remember things with a word association. Molar mass equals dirt over P. And then you're going to plug in the gas density, 1.95 grams over liters, times the ideal gas law constant. Okay, before I write that down, I'm going to look to see what my pressure is, 1.5 atmospheres. That tells me then that I want to use 0.082 latam camol, and then temperature of 300 Kelvin. So now if you look at the units of this, remember, on your test, as long as everything's done where the units look the same, like for example, if you use liters, that this is liters, if you use atmospheres, that this is atmospheres, you don't have to actually sit down and go cancel out the units. Nobody's going to be looking at that. You have to make sure that when you get a final answer by multiplying this, that you put grams per mole. So even if you can't spot how you get grams per mole, it doesn't matter because molar mass is measured in grams per mole. So you do all the math, but as your teacher, it's my job to show it. Liters cancel out liters, Kelvin cancels out Kelvin, atmospheres cancel out atmospheres. Remember, this is a numerator and this is a numerator. So they're canceling each other out since one's in the numerator and one's in the denominator. So what you end up with is grams and moles. So it does work out. Don't worry about it. 30, hey, there it is, oxygen. My subconscious must have known that was going to be the answer, which is why I brought it up in the explanation at the beginning of the section. This is a homework question, and I can see it's already 8:45, and I did not want to keep you guys till 9:30. So, and I've got to still go over another section. So I think I'm just going to save number 16 for homework. I just want to point out what makes this one difficult is that they're talking about rates, right? They talk about liters per minute, and they want to know what mass per minute is produced, okay? And so you're like, I don't know those things. Mr. Person never taught us anything about rates, volume per minute. What are you talking about? Volume over time? What the heck is that? Here's an easy answer. Just assume 1 minute. Then, if everything is based on 1 minute, you can say that there's 500 liters of carbon dioxide and 600 liters of ammonia. And the fact that, I'm going to at least write this much down because I do want you to be successful, that if it says this, and they tell us that this is 600 liters and this is 500 liters, and we want to know what mass of urea, that's this big long chemical formula. If you want to know what mass of this is produced, you should be looking at it going, ah, this reeks. Not just because it's urea, which is in urine, which reeks. It reeks of a limiting reactant problem, doesn't it? One of these two is going to limit the reaction. Remember that chemical reactions deal in moles. So therefore, you need to figure out how many moles of each reactant are there in 1 minute so you can see which one's going to run out first, okay? So I'm going to plan on going over that next time we're together, but I don't know for sure that number 16 is going to make it into the answer slides because I already made the slides for next week. But the answer is here because we were supposed to go over it in class, but I don't want to keep you guys. So you could always go back and look at it yourself. And if it didn't make sense, then you need to tell me during the Zoom to go over question number 16 if it's by chance not already in the notes on Thursday. All right, a whole bunch of you said, I don't know who P-Man is either, but yeah, it would smell like urine. It would smell like if you walk down the wrong street in downtown Los Angeles. Some of the streets really, really reek of urine. But I've already told you guys before, if you ever have a chance to travel into downtown Los Angeles, do it. You're going to find, and when the pandemic is finally under control, you should go down to downtown LA, because we have one of the absolute best downtowns, and it's an hour and a half from our houses. Second thing is also downtown Riverside is a great downtown also. It's not nearly as good as downtown LA because it's just a smaller town, but it's still a great downtown. It's pretty. It's got a lot going on. There's a lot of college kids. It's a college that I recommend you think about going to. If you can live on campus at, I don't even know what that means. It's in Europe. It's in urine for Mr. to possibly him. I don't even know what that means. UC Riverside, great school. If you go there, live there. And what's nice is while you're there, if one night you're just sitting there and you're studying and your roommates are pissing you off, you could come home. You could come home for one night, right? And then of course, you're going to be sick of your parents and little brothers and sisters within one day anyway. You go back to school the next morning and you don't even miss a class. So it's a perfect place to go because it's close by, but yet at the same time, it's out of your parents' reach, all right? So think about UC Riverside. It's got a great nightlife. A lot of good bands coming out of the kind of that lower part of the IE also. So just an idea. Dalton's law of partial pressures is about one of the easiest things that you could learn in this class. Basically what we're saying here is if you have a container and that container has, maybe let's pretend it has N2 in it, and it's got O2 in it, and it's got H2 in it, and maybe we could put some helium gas in there as well, that if they aren't chemically reacting with each other, which they won't be, then those gases, as they go around, they collide with each other and bounce off the walls of the container, and they all together add up and create a total pressure inside that container. But they themselves, if all of a sudden, watch this one, this is really neat. Hey, where'd everybody go? If just one of those gases is in there by itself, it has a pressure that's completely independent of everybody else. So each gas contributes to the overall pressure with their own partial pressure, okay? Now, you'll notice who this is named after. Named after Dalton. I can't get the pen to come back. There it is. Named after Dalton. And what do we remember about Dalton? He was like the first guy in modern chemistry. In other words, this law was discovered when they really didn't know a lot of chemistry. So this has to be something relatively easy, and it is. It's as easy as what it says there, okay? I don't have any idea what you guys are talking about. I did see a good movie this weekend. My wife was all bent out of shape because she had ordered a home, it's gonna sound weird, a home brewing taste kit. In other words, somebody put together for like a fundraiser, a whole bunch of different beers, and then they would mail them to the people, and then all together online, we would all do a tasting of all of these beers. And so she ordered it, and the tasting was for Saturday, and it never came. So she contacted them on Friday and they said, oh, I'm sorry, we screwed up. So she was all bent out of shape on Saturday. It took it out on me and everything. It's like, I didn't do anything, right? And so anyway, so I'm like, oh, okay, I got to figure out something. So I'm like, well, let's watch a movie, right? It's about Halloween time. Let's watch a Halloween movie. Every single movie about Halloween is scary. And she doesn't like scary movies. So eventually I found Sleepy Hollow, right? Johnny Depp from like 1999, back when, you know, the guy's still gorgeous, but back when he was even more gorgeous, all young. That was really good. I enjoyed it. It wasn't too scary. You know what? I saw Hubby Halloween and the things, and I've seen too many Adam Sandler rom-coms lately. Not lately, but like maybe since the pandemic. You know, we've been, without being able to go down and see live music down the hill, what are we going to do? So a little bit of that has been, we have actually watched a few more movies. And apparently that's where Adam Sandler went, was into rom-coms. And it's like, I would be okay with rom-coms, but come on, make them funny, right? First of all, Adam Sandler really isn't that funny. Sorry if I offend you if you are somebody who thinks he's funny. I grew up with Adam Sandler. He was Saturday Night Live when I was in college. And at the time, all of the skits that he did, I'm like, this guy's not funny. They're all the same thing. All it is he makes himself laugh. So in the middle of a skit, he screws it up. And so everybody laughs because they think that's funny. I don't really find that funny. So sorry if I offend anybody who finds Adam Sandler funny. I did like the movie about 10 years ago. He did a movie where his wife, and he was tempted to have an affair, and his wife ended up actually having an affair, and he had this daughter that he was really close to that was kind of homely, and that was a really touching movie. I think I actually might have had a little tear at some point during that movie. So I should give him a little credit. And I also found Billy Madison, the one where he has to go back through school. I found Billy Madison funny. That one was good. When he's trying to be funny in front of all the kindergartners. Little Nicky. I like Little Nicky also. So you know what? I guess I am an Adam Sandler fan. Never mind. All right. You have a test question like this, but it won't be as pretty. I don't think I liked Happy Gilmore. Is that the golfing one? I don't remember. But they got to be all the same. It's the same thing with all of his murder mystery. Is that the name of it? Or is it a murder mystery? Because if so, I'll look for it. Because we like the murder mysteries. Knives Out. Knives Out was really good. Okay, I'll look for that one. And if the wife doesn't like it, I'm gonna blame it on you. Fair enough. Perfect if it's on Netflix. All right. You have a test question like this one, but it's gonna look more like this question. This is exactly what the test question looks like. I took this exact picture and I just changed the number of particles of each gas, and then I changed what these numbers are over here in the problem. But because I gave you this one and you already took the time to write it down, let's write it down and let's do it. Okay, so here's what you're gonna do when you solve these problems. We're gonna open up these valves, right? We know that in real life, this is why I picked this problem. In real life, you can't just breathe straight oxygen if you go down into scuba diving, because the problem is pure oxygen will burn your lungs. Your lungs have evolved to be able to have the inert gas of nitrogen mixed inside of there. I'm not sure why they don't use nitrogen. They probably do. I'm not a scuba diver, so I don't know how they exactly come up with their ratios. And I know they have to change the ratio based on how deep you go. If you're going to go really, really deep scuba diving, they're going to change the ratio and probably make it a little bit more oxygen rich. But don't quote me on this because I don't know the exact science of all of this, right? But here's what you're going to do. When you open up the valves, what happens is there's a total of 5 liters of container here. So we're going to pretend that only this gas is present and that there is no helium gas here, so that if you open up the valves, the oxygen is going to start coming out of this tube. Some of it's going to go down into this tube, and some of it's going to go through this tube and go into this tank too. So we want to know what would be the new pressure of the oxygen if instead of only fitting into 2 liters, what if it fit into 5 liters? This is just a simple Boyle's Law problem. In Boyle's Law, we say that, so I'm going to say P for the O2 times V, that's going to be way too many subscripts, equals P2 times V2. Okay, so if you were at you're at 5 atmospheres in a 2-liter container, and all of a sudden you allowed this to fill up a total of 5 liters. All right, now the fact that I put that, I better put the units next to this too, because if anybody's writing this down and studying it later, okay? So by allowing that gas to expand to a large, hopefully you guys are able to still hear me. Right now it's saying my internet connection is unstable. Hopefully you can hear me. By expanding to a larger volume, we make the gas pressure become less. It went out for a second, good. Okay, now let's do the opposite. What happens if you take the helium, so this was for the oxygen, Now for the helium, let's do the exact same thing. If there was no oxygen gas and you opened up the valves and let the helium spread to all of the containers, then what you're going to have, P1 times V1 equals P2 times V2. This is called Boyle's law. The reason why we're not including the temperature is because we're going to assume the temperature stays constant because they don't mention it. So I just leave it out of the equation from the get-go. And then we would say that 10 atmospheres times 2 liters equals what pressure if we now allow it to go to 5 liters. 20 divided by 5 is 4 atmospheres. Okay? Now, Dalton's law of partial pressure says that each gas contributes to the total amount of pressure. So all we have to do is add those two partial pressures together and we get the total pressure. It's that simple. It's really, 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 really simple. I should see everybody get question number, example 2, correct on the test, because I'm telling you ahead of time, this is a test question. I wrote that in permanent writing because it was like a test question before. And when I was dismembering last year's in-class test, I'm like, I can't take this one away. This one has to stay in there. So you have this exact picture. The difference is every test gets 3 different gases with a different number of particles. And then every size of the container is different. I'll even let you know that each of the 3 small containers are all 1 liter. But how many particles are in each is dependent on the test. Sorry, had a brain fade there for a second. Here's why we know what's going on. Neon gas is at a pressure of 2 atmospheres. That's down here. And then what it says is the number of particles in each container is representative of their pressure. So if 2 particles represents 2 atmospheres, 1, 2, 3, 4, 5, 6, 7, 8 represents 8 atmospheres. And 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14? Did I count right? 14, yeah. 14 atmospheres. Okay? So then it starts by saying, what would happen if you opened up valve 3? So you turn this valve open so that the gas can escape into the center container. So we could say then for neon, when you open up the center container, we would go with P1 times V1 equals P2 times V2. 2 atmospheres of pressure times a volume of 1 liter equals now a total. If this is a 9 liter container, we're now at a total of 10 liters, not 9, 10, because you also have to include the original container. The gas is going to still occupy that container as well. So P2 times 10 liters. P2 equals 2 divided by 10 is 0.2. Yeah, 0.2. Sorry. Too early in the morning for me too. Okay. Now, if all 3 valves are opened, so this is the answer to what we'll call part A. If all 3 valves are opened, then each gas is going to occupy each container. So I still have to redo this for neon. Because for neon, now we would say that in P, I'm not going to write this formula down over and over again. It's probably on the slides if you really want to do it yourself. I'm going to just put that 2 atmospheres at 1 liter size container now has the ability to occupy a total of 9, 10, 11, 12 liters. Oh, put it in the wrong place. So its pressure reduces even less than 0.2. 2 divided by 12 is 1/6, like 0.17. Let's not call that P2 because we're going to use this over and over again. Let's call that P and E. Then for HE, it's a total of 14 atmospheres in 1 liter is now going to expand out into 12 liters. 14 divided by 12. My gosh, who picked these problems? Couldn't you make the numbers be nice and round? I tried to on the test. So you shouldn't need a calculator. 1.17. And then finally the H2. 8 atmospheres times 1 liter that it's in originally. Open up all the valves. The hydrogen gas can expand to the entire 4 containers that are there, which is a total of 12 liters. And that gives us the pressure of the H2 is 8 divided by 12. I believe that that's 2/3 or 0.67. Then Dalton's law of partial pressure says that add those 3 numbers together and you get what the answer slide says. 2 atmospheres. Good time. I know I just wrote fast. All the answers are there. You understood what I said, which means that you can kind of still treat this as looking at the notes later. So I can go forward because we still have to talk about mole fraction. Then finally we're done. I feel bad for mole fraction because I treat it as a redheaded stepchild in both honors chemistry and in AP chemistry. It gets stuck at the end of Dalton's law of partial pressure in both classes. And in our normal classroom setting, after we've gone over that tremendously long homework number 2, and then we go over Dalton's law of partial pressure, no, that's not even true because we would have gone over the first section from here, the gas density. It must be that this always falls on a Wednesday because we end up not having enough time to really give mole fraction its due. And part of me says it's really simple. Mole fraction is just the fraction of the moles. And in PubNert, PV equals nRT. If this stays constant, this is a constant, and the temperature stays constant, then what that tells us is that the mole fraction equals the partial pressure fraction, right? So whatever fraction of moles is there makes a fraction of the total pressure as well. And so that's why they put these 2 sections together, is because these 2 formulas complement each other so well. So I'm still treating it like a redheaded stepchild because I want to be done here very soon. What else do I need to say about it? Is there's a question. And I got to admit, this question, I almost feel bad because when I wrote the test, I guess I started this question on Saturday and finished it yesterday. Last night, I was going over these notes real quick just to see what I had written in the red text boxes because I didn't want to forget any of that stuff because I knew I didn't include it in these inner right slides. I went and I looked at this one and went, oh crap. One of the test questions I wrote is so similar to this. Will I change it? So then of course I'm like, I don't have time. So you might get this question on your test, but it's not this exact substance, but gosh, it looks so much like this problem. All of them look like this. It's just that most of them are similar to the AP question that I got this from. And all of these are very similar to the lab that you're doing on Wednesday. So I'm going to go over this real quickly. I apologize that I'm not really giving you enough time to copy this down, but I'm going to start going over it. If 2.20 grams of potassium chlorate was decomposed, what would be the theoretical yield of O2 in moles? So by looking at this question as an FRQ, all of a sudden you might possibly look at part A of this one and go, I can't do this. I can't do this. I don't know how to do this. This is outside of my wheelhouse. Yet really this is no different than what you did for homework last night, right? It's just it's written in an FRQ form. And the other thing is it didn't go all the way out to liters. It stopped at moles. So if you have 2.20 grams of potassium chlorate and you want to know how many moles of O2, that feels like a stoichiometry problem, right? So I'm going to put a big long conversion table line, and I'm going to put moles here. I think you guys are sometimes putting stuff in the chat. No, nothing's new there. Sometimes the chat, I don't feel like it shows up on my little computer, but it looks like everything's here. So I haven't missed anything. So if I didn't address something, if you guys are sitting there going, oh, so rude that I didn't answer something that you said, please understand that I'm looking at my Chromebook to read the chat. I'm not looking at this one because the chat keeps disappearing behind the InterWrite slides. So if you say something important and I need to see it, just unmute and say, hey, look at my post. Say it nicely. Get out of grams of KClO3, get into moles of KClO3, then get out of moles of KClO, sorry, I'm not writing very well because I'm in that nervousness of going too long, moles of O2. Balanced chemical equation says 2 to 3. Periodic table tells me what the mass of KClO3 is, 122.6. And then my calculator tells me 0.0269 moles, significant digits, 3. I'm happy with that. Here's what I do on the test. I point arrows at this, and I write SD, and I write units. And then I put over here 5. So the question's worth 5 points. You show me some work, you get 1. Like if you tell me your givens. You show me some work, you get 2. You answer it, you get 3. You put the correct significant digits, you get 4. You put the units, you get 5. Easy, huh? If 0.650 liters of gas was collected by water displacement at 22 degrees Celsius and 754 torr, what is the experimental yield of O2? The vapor pressure of water at 22 degrees is 21 torr. Say what? Let's go to the next slide where we can see a picture. Okay, here's what happens. This is going to be in our lab too. I'm going to heat up sodium bicarbonate, just like you did last year. It's the same lab. And except for the difference is because I have the benefit of time, I heated it really, really, really slowly so that I was sure that I could kind of, I don't know, stop the expansion due to heat. So as you heat this, it decomposes. And then as it decomposes, the gas, because of pressure, force themselves down this tube and then up inside this side over here, which is full of water. And so now our oxygen gas is inside of here, right? And it's starting to accumulate. But there's a problem. As it pushes the water out of the container, water likes to evaporate, right? Water is just volatile enough that water molecules will also accumulate up inside of here. In other words, are you hearing this? The total pressure inside that container is not due completely to the oxygen that we've collected. So if the experiment says that you can find the number of moles of oxygen by taking PV over RT, which is a true statement, you've got to put the correct P in there. Okay, what liters do we have? 0.650. Ideal gas law constant. Everything's in torr. Why don't we keep this one in torr just for practice like our test? So I'm going to use 62.4 torr mole. Don't worry, we're almost done. And then a temperature of 22 degrees plus 273 is 295 Kelvin. So now the only question is, what do I put in for P? I am not going to put in 754. That's because Dalton's law of partial pressure says if water is present, then the pressure inside of the container is a combination of whatever gas you've collected plus also the water that is evaporating. So 754 equals PO2 plus 21, because somebody has already figured out what the partial pressures for water is at every single temperature. So you subtract 21 from 754 and you get that PO2 equals 733. Now, if you're looking ahead at the next slide, you're going to see that I've already converted this into atmospheres so that I can use latim per mole. I'm doing this on purpose because on your test, you can speed things up by just leaving it in torr. Okay, You ready for this? What are the units of your answer? Good answer, moles. Did you figure that out by crossing out units? No, you figured that out because N is measured in moles. So you don't need to go through and cross things out. You just leave it like it is, because as long as everything's compatible, everything cancels out and it just leaves moles. Whether you converted to atmospheres like I did or left it in torr, you're going to get 0.0259 moles. Let's go back to that slide and put it on here. 0.0259. Look at that. Close. Theoretically, we get more than experimentally. All right. Thank you for your attention. You guys did very good. That was a long time. Don't forget you have 2 homework assignments tonight. It's written in the chat, so I don't, or in the classroom, so I don't need to say anything more. I'm going to close this to get you guys going to your next class, unless you got something you need to say to me. Here, I'm going to turn this off at least, and then if you want to say something to me, you can